not in a hurry. And so tomorrow we start at 9.
I think it's the
yes,
best.
Okay, for me it's perfect.
So we end at 10 maybe. So you can go to the railway station.
Yeah, for me. Yeah, perfect.
I have to record this.
Yeah.
Okay, just before starting, I recall that tomorrow the lecture of Professor Dimca will start at 9, not 9:30, because he has to go. So, so please be here at 9 if you want to attend the lecture. Thank you. And okay, so I think for those who are late. Tomorrow, Professor Dimca will start at 9. Okay. Okay, let's start.
Okay, thank you very much. So I will recall the notations. So I have a hypersurface V in some projective space. And we assume that the singular set is a finite set. And we denote U the complement and I will draw the picture. So assume that this is V. These are the singular points. And yesterday we have looked around each point of this type, and we have considered the ball of radius epsilon, let's say, center at such a point. And we have described the top cohomology of the complement in terms of differential forms, at least when all the singularities are weighted homogeneous. So I have not mentioned yesterday, but this cohomology group have also mixed-Hodge structures. And in the case of weighted homogeneous singularities, the mixed-Hodge structure goes back to Steenbrink, and it is very explicit. That is, we have some analog of Griffiths results describing the Hodge filtration in terms of order of the poles. And in the general case, we still have mixed-Hodge structure, but it's more complicated to describe them explicitly. Okay? And so you see that we have rather good information at each local singularity. There is one problem that at each local singularity we have to use some local analytic coordinates which are adapted to this situation and which have nothing to do maybe with the coordinates we have in the beginning on the projective space. And so in this talk, I will start with some topology. So first, how to relate these local complements, the topology of these local complements, to the topology of U. And finally, I will show how to bring in the algebra, how to bring in the polynomials, because we want to describe at the end the Betti numbers of V in terms of some defect of linear systems. So we need some polynomials around, and for the moment there are no polynomials. Okay. So some more notations. V star will be V minus a singular locus. P star will be the ambient space minus the same finite set of points. And of course, you see that P star minus V star is again equal to U. Okay? And so now what is the advantage of all these notations is that V star is a smooth hypersurface in V star. And so we have an associated Giesing sequence. And using this Giesing sequence, we can prove easily the following lemma. So I write first the Giesing sequence. Which has the following. Okay, and all these spaces are algebraic varieties, so they have mixed host structure, and this residue morphism has Hodge type -1, -1. This is the first claim, which is obvious. Then the uneasy calculations show us that there is not much difference between the cohomology of the projective space without finite remaining points and the cohomology of the projective space, the usual cohomology of the projective space. So we have natural isomorphism for K. We are essentially interested for K in the middle ranges, so around N. So this will be okay for us. And another fact that the morphism induced by inclusion this is alpha. If you like, alpha is trivial for the same range. Okay. And so as a corollary, exactly as we got in the smooth case, we have the following result, that the residue morphism will give us an isomorphism where by definition this primitive cohomology is nothing else but the cokernel produced by the inclusion. Okay, and so so this corollary comes from this exact sequence, and so exactly as in the smooth case, we can relay the topology of V star to the topology of the complement. Okay, and so now there is another long exact sequence. Yes, sorry. Thank you very much.
Is trivial, you mean the zero having?
Yes, zero. The zero morphism. Trivial means zero morphism.
Maybe I'm missing something, or it can be zero in degree zero, for instance. I don't understand.
Yeah, you are right. So maybe. So. You are perfectly right. It's not zero there, but it's zero otherwise. For instance, in A1, in A1, why is zero? I just explained it geometrically. It's zero because for k equal 1, let's say we assume, for k equal 1, if we assume this, is nothing to prove because H1 is 0, right? Now I will prove for k equal 2. For k equal 2, we have something to prove because we get one-dimensional vector space. And we know that this is spanned by the chain class of the canonical line boundary, O of 1, right? And O of 1, when we restrict to the complement of any hypersurface, a power of it, O of D, has a section. And so the chain class is torsion. So because we work here, the coefficients are supposed to be Q. So I forget to say those. So coefficients are in Q. And because of that, this morphism is trivial for k equal 2. And you can continue in this way. Okay, thank you very much for your remarks. Okay, so we have a long exact sequence of Minkowski structures. So for the moment, I repeat that we have some Hodge structures in the background. I will not use it except one key point. So in one key point, I will use these Hodge structures in the background. So I have a long exact sequence, which is the following. Is a cohomology with support, and I will explain what it is if you are not familiar with this. Okay, so by definition, this is nothing else but the relative cohomology of V minus sigma, which is V star. Okay, and so now I'll consider consider the case when n minus 1, which is the dimension of V, is strictly bigger than 2. This is a case in which we are interested because we are mainly interested in threefolds. And so let's see what we can do in this case. we can start with Hn of u, and then we have first the isomorphism R, which is described over there. And then we have the morphism delta. Then we go to Hn0 of V, which I recall you this is an interesting part for us. Because we have two unknown cohomology groups, a big one and a small one. This is a small one, and so if we are able to compute this, we are able to compute both. And then if we continue, we have here Hn0 V star, but this is isomorphic, again using the lemma, to Hn plus 1 of u, and this is 0 because u is an affine variety of dimension n, and so is homotopy equivalent to a CW complex of real dimension n, and so when I take n plus 1 cohomologies, this vanishes. And so I can write here a 0, and so I get some surjective morphism at this stage. Very good. And so now let's look more carefully to this cohomology group and try to relate this cohomology group to the local complements, because here we have the global complement. Now we will put in the picture the local complements. So this is just a definition. And now in algebraic topology, as opposed to algebraic geometry, we can localize very strongly, and this localization is done by excision. So we have an isomorphism here given by excision. So essentially, if I come back to this picture, I have to compare the relative cohomology of V and V minus these special points. And so the excision tells me that I can throw away everything that is outside the balls because nothing interesting happens outside the balls. All right? And so the excision will tell me that this is a direct sum of Hn. I will denote Bi, the ball corresponding to the point Ai. So Bi intersection to V, and here Bi intersection to V star. Okay, and so the sum is for I equal to 1 up to P. And what is important now is that this space here is contractible because it's a cone over the link of the singularity. And so I can replace this morphism by, if I write the long exact sequence of this pair, I can replace this by the direct sum of hn minus 1 bi intersecting b star. And now we are in the local situation. So we have the ball. Imagine that we have the ball bi minus the point ai. Inside here we have this intersection. So this is bi intersect b star. And we can apply again a result of this type. And we can replace this by direct sum of hn bi minus v. And these are exactly the local complements. And so you see that this local cohomology group is nothing else but the direct sum of the top cohomology of the local complements. Okay? And so if I put everything together, what I get? I get the following exact sequence. So I start with the cohomology of U. And then if I take this composition, and if I compose with all this isomorphism, I get a mapping of this type. But now it's very easy to imagine what this map is, because just think that we represent here a cohomology class by differential form. What can we do to get the image? We just take the restrictions. And this means that this morphism is just a direct sum of the inclusions, where GI is the inclusion of the local complement bi minus v into Pn minus v, which is u. And so the whole composition, which looks complicated because we have a lot of isomorphism, is in fact very simple. So sometimes the nature makes us gifts, and this is a gift of nature, the fact that this composition turns out to be so simple. And so then we have this morphism, and then we have here 0. Okay? And so now the main result is that this sequence is exact. Moreover, it's an exact sequence of mixed Hodge structures, because all the elements here have mixed Hodge structures. And this means that, in particular, for any s, for any integer s, we can apply, we can take the Hodge filtration everywhere and still get an exact sequence, right? And now if you look carefully at all this isomorphism, because here we have something of type -1, -1, it turns out that in fact this morphism here is of type -1, -1. And so to get really an exact sequence, we have to shift the Hodge filtration by 1 at this point. Okay, so this is this is this is the result. Now, we have some nice description of the cohomology group in the middle. This is what we explained yesterday, especially when the singularities are weighted homogeneous. But for the moment, we have no idea how to describe the cohomology of the complement U, right? So now I will explain that maybe we are not able to describe the cohomology of U, but we can describe a larger space such that the image of the first morphism can be replaced with a very simple morphism. So our aim is to replace the first morphism, which is pretty much unknown, with a simpler morphism such that the sequence is still exact. And then the unknown group will appear as a co-kernel of a very simple morphism. Okay. So until now it was simple topology, let's say. And from now on we enter really in algebraic geometry, and tomorrow will be more of algebraic geometry and commutative algebra. So we are interested in U, and we moved from V to U because U is smooth. Moreover, it's an affine variety, as we have already used this fact for the vanishing of hn plus 1 of u. And we know that for smooth affine varieties, the cohomology of u can be computed using a very explicit complex. This is the global Durham complex. Of u, and this is a theorem by Grothendieck. So now I will explain you what is the global Durham complex for the complement of a projective hypersurface. Yeah. So H0 of u in just the global sections of the regular functions. So these are just and everybody knows what this looks like. It looks like quotients of the following type: G over Fk, where G is a homogeneous polynomial. You recall my notation for the polynomial ring S. And G should have a degree equal to dk, because we want this to be homogeneous. Everybody knows this fact, right? Okay, now let's see what is A1 of u. A1 of u is something similar, H0 of the one form of u. But now it becomes a little bit more complicated in the sense that not everybody knows how to describe this explicitly, but it's not so complicated. So it looks like that we still can put here arbitrary denominators, and we have here a morphism delta, which I will explain in a second. Here alpha, where alpha belongs to omega 1 Cn plus 1, and with a degree kd. So what is delta? Well, delta is a unique S-linear morphism going from global polynomial forms, let's say, going from so omega k plus 1, I can put here Cn plus 1 if you like. These are just differential forms in the variable x with polynomial coefficients. And k is a degree. And delta should satisfy the following condition. It is S-linear. Delta of dxi is equal to xi for all I equal to 0 up to n. And delta of a product of two differential forms satisfies the usual rule, Leibniz rule. And this is called a contraction with Euler field. the Euler field is this vector field. And all this theory can be done for weighted projective spaces if I put some weights where it should be. And you can find this in many places. And so the whole idea is that these objects are very concrete objects, right? We start with a polynomial form. We apply this morphism delta. And then we take care to have as many poles as the degrees of the numerator. Okay, so I hope now this is clear what I mean by the global Durand complex. And there is a differential acting, of course, here. I won't go into the details. So what is important is that...
so you only need the algebraic delta section.
Exactly.
That's the deal.
Yes. So an element here is a formal sum of some polynomials times some exterior monomials, where alpha is a multi-index. So A alpha are polynomials, dx alpha is dx Okay, good. So we can express the cohomology as the cohomology of global sections of this Durand complex. And now this complex A of U comes up with filtration. And this is a decreasing filtration. I will write you in a second what does it mean. It's an infinite filtration. So S can take values which are negative. And now I will describe you this filtration. So I can give you a formula, but instead of giving you a formula, I prefer to tell you what the filtration does on each term of the complex. And so the complex has terms of degree 0, of degree 1, and then of degree n minus 1, of degree n. So in degree n, of course, I put the differential forms of degree n on U. And so Pn minus 1 is clear, it's just a 0 subcomplex, no problem. What is Pn? In Pn, you put 0 everywhere, except the last position. And in the last position, you allow the smallest poles. The smallest poles means poles over the 1. And what is Pn minus 1? You put 0, 0, 0, and then you have two non-zero terms. For n minus 1 forms, you allow the smallest possible poles. And for n, you allowed a little bit more poles. And this is done in order that you have a differential preserving this subcomplex. And so I will write what does it mean PS for the last term. So what is here? Well, here we have to put forms having a pole with this order. So you see for S equal to n, this is correct, and this is correct like that. And so actually this can be written as H. I introduced yesterday or the day before differential form of degree n, omega, with some alternating sums. And so you see that I have a very clear description of the filtration, at least for the top degree forms. Okay? Now, what happens when you have a filtration on a complex? What do you get? We get two things. First of all, we get a filtration PS on the cohomology of U just by taking, so if you want to know what does it mean, PS of this is just the image of, you take the cohomology of PS of A, and you inject, you transform it by the inclusion into the cohomology of A. And this filtration is called the pole order filtration. Okay? And you get a second ingredient, which is a spectral sequence. Which is in fact an E1 spectral sequence. And so tomorrow I will discuss more about this spectral sequence. Today I will concentrate on this pole order filtration and how can this be used to solve our problem. Okay, so questions are welcome. So I will write again the sequence that was on the blackboard. Okay. So you can imagine that I have a similar I can do the same trick which I have done for the global complement. I can do for the local complements, because local complements are smooth Stein manifolds. And for a Stein manifold, Grothendieck's theorem still works. And so I have such a morphism. And now let's come back to the pole order filtration. Yes, one has to use holomorphic forms, and one has to work with actually germs of holomorphic forms. But most of the time I will restrict myself to weighted homogeneous singularities, and then you can do everything with polynomials because of the C-star action. Okay, so results on pole order filtration. The first result, which is easy, is that if V is smooth, the two filtrations, the pole order filtration and the Hosch filtration, coincides, and this is essentially Griffiths' theorem. And this works very well for smooth hypersurfaces in projective spaces, but it works also very well for quasi-smooth hypersurfaces in weighted projective spaces. And because our weighted homogeneous isolated singularities are cones over such a situation, we have equality here if we assume are weighted homogeneous. So in general, there is a theorem which I proved a long time ago with Pierre Deligne. And this theorem says that in general, so for any hypersurface, not necessarily with isolated singularities, the pole order filtration is bigger than the Hosch filtration. So we have such an inclusion, and in many cases is strict. And there are a lot of papers So a discussion on cases when the equality still holds for singular hypersurfaces. This can be found in paper by Moritico Saito and Moritico Saito and myself. So there are cases when the two filtrations coincide, but in general they are distinct. And so let's come to our
But there is a characterization or just some examples?
there are general results. For instance, if the singularity, if the hypersurface has isolated singularities, at each singularity you can compute the Arnold singularity index, and then depending on this index, we can tell for which S one has equality. And for instance, for nodal hypersurfaces, these results are very strong. We can say exactly when we have equality. Okay. So there are a couple of papers. Okay, so now where are we now? So what is clear from what we discussed until now is that I can take the polynomials of this degree and for each polynomial h, I can consider, so for each polynomial h here, I can consider that differential form, takes the cohomology class, and I am sure that I get a surjective mapping. Right? And I compose this surjective mapping with this mapping, and because of this inclusion, I can show that this composition up to here has the same image as this morphism. And so finally what I get a mapping starting from something very precise into a direct sum of spaces, which can be sometimes computed, such that the co-kernel is the cohomology group of interest to me. And I will explain what happens for nodes. So what happens for A1 singularities in even dimension. So in this case, we have shown that if we take S equal to M, the sum of these spaces this is one-dimensional, and in each space the generator was given by such an element where G is a local equation for okay. And here we have our space of polynomials. Let's call this capital N to simplify. And the map here is just to take a polynomial and you evaluate at each of these singular points. But if I call this element alpha I, you see that what I get here is H A1 times alpha 1, H A2 times alpha 2, and so on till the end. And so what is the dimension of this is just a co-kernel. One can show that this is just a co-kernel of this map. Let's call this theta. And what is the dimension of the co-kernel is exactly what I call the defect of the linear system of polynomials of degree n with respect to the set of singularities. And this is by definition what the number of nodes, because each node imposes one linear condition on the polynomial, and minus the dimension of the space of homogeneous polynomials of degree n divided by the idea of polynomial vanishing. So En is a set of polynomial h in Sn such that h ai equal to 0 for every I. So the co-kernel is dimension of this space minus the dimension of the image. The dimension of the image is exactly this. And this is the dimension of the space. And this is how the defects of linear systems are related with the Betti numbers for nodal hypersurfaces in even dimension.
So the defect is not zero if only this singular point imposes dependent condition.
Exactly, exactly. So if we start with just a few number of nodes, then the defect will be 0, and so nothing interesting happens. To have something interesting, we need a lot of nodes. So tomorrow I will start with some concrete examples. I will describe Chebyshev threefolds in P4, which are some hypersurfaces with a lot of nodes. And for them, we can even give some formulas for this defect. And then in the second part, I will discuss the spectral sequence and why it's necessary to look at the spectral sequence if we are interested in more complicated singularities. This is the rough. Okay, and so in fact, we can state what we get in the end is not only the dimension of this vector space of this cohomology group, but we can also decide that so in the case when the dimension is even, we can also prove that this cohomology group, I write here 2m because we are in the even case, is of type Hodge type M. And so we have an information on the Minkowski structure on this cohomology group as well. And this comes from the fact that all the local cohomology group have this type, and so when we take the co-kernel, we stay in the same. So the local cohomology group, such local cohomology group, actually they have type m plus 1. And so with this shift in the Hodge filtration, we get exactly this result. Okay, so it was a little bit quick at the end, but we will come back tomorrow, promise.
So, are there any comments or remarks?
Yes.
Maybe you will know anyway, but there are these numbers of hypersurface of degree something and has at most a certain number of nodes.
don't know. So I know that there are results by Cheltsov and maybe other people telling that if the number of nodes is smaller than something, then the defect is 0. Right? And I'm not sure I can recover these results with these techniques. These results are very good for computing examples. If you have an example of hypersurfaces with nodes or other singularities, you can try to use this approach to compute effectively the Betti numbers. And in general, I don't know. Might be possible, but nobody has done this until now.
So if there are no other questions, then thank you.
Okay, thank you.